Convolutions, by the way, are a class of things that contain a lot of other things. So you can choose, like, the lots of things you can phrase as a convolution, but that doesn't mean that is a good way to formulate it. And this one has a pretty clear thing that you can do. All right, 4 o'clock. Is it mic on? I guess mic's on. 4 o'clock, time for class. Welcome to the new room. Per request, here is a little outline of what we're doing today. Also, we have our office hours. Just mine are locked down so far, so the SI section and mine are locked in. But besides that, the other TAs, like one TA has decided, but not all of the TAs have decided on their office hours yet. We'll announce that soon. But mine are going to be, this is directly after the later discussion in the same room as the later discussion. So if you're in that one, just stay in that same room if you want to do office hours. And if you're not, that's what it is. Cool. So because I think some people are probably going to get confused going to the other room, we're going to spend a little bit of time on review. Yes, Tomas?
Oh, just to advertise, my sessions are on Tuesdays and Thursdays at 7 p.m. The details of the room are on Piazza, it's at the Boy Library.
Right on. So you write it under there. Actually, can I have the black one here? You can have blue. I'm going to use the black right now. Okay, cool. So SI sections are going to be put on there. You can look them there too. Okay. So today is a pretty interesting and important topic for understanding recurrences. Today is going to be basically, we're going to tie a bow on understanding recurrences and understanding divide and conquer. We're going to have one more divide and conquer lecture after this where we're going to look at a pretty interesting algorithm. That's going to be on Wednesday. It's going to be Strassen's algorithm, if anyone wants to look into that ahead of time. It's a cool one. And it's definitely the coolest divide and conquer one that I think is in the scope of this class, so do like it. But I'm going to spend a little bit of time reviewing merge sort just to make sure that everyone understands the recurrence, where it comes from, and all that, and then we're going to talk about more general recurrences and how to solve them. You two, can you close your laptops too? Yeah? Thank you. Okay, so merge sort. The basic idea of merge sort is that we are going to divide and then we're going to conquer. That is, we're going to take some problem of size n, we're going to split it. How many times do we split it? 2 times. And each of the subproblems are going to end up half the size. So we're going to end up with each of these half the size. And for each one of these iterations, so when I make a call to merge sort, right, it will recursively call 2 subarrays, or 2 subcalls to merge sort, which are these 2 in this case, right? And then it does the merge step. And how much work does the merge step take? I think we've covered this pretty well, so hopefully this should be quick. It's O of n, right, or n minus 1 as we've talked about before, or some other thing roughly in that range, right? So when I make the call to merge sort on the full array, it will call the 2 subarrays, and then it will do a merge that takes O of n times. So we say that this level of my recurrence is going to do how much work? O of n. So this level will only do O of n, and then it will recur 2 more levels. O of n, right? And I'll say just n to make it simple for people, but all these things remain true if I make all of them O of n. It's fine. If I just do everything as upper bounds. Anyway, so then in this level, right, we make 2 recursive calls. We've already established that when I call merge sort on something that is of length n, it does n work. So if I make a call on something that is n over 2, how much work does it do? N over 2. And how many times do I do it? 2 times. Cool. I'm just drilling it home, make sure everyone is 100% on this. So this will end up being 2 times n over 2. And what we notice with merge sort is that as we continue, as we keep doing this, it turns out that every single one of these levels, what's this next one? Does anyone know off the top of their head? Yeah? Anything? Anyone? Next level? Utkarsha. So it's going to be 4 times n over 4, and it turns out that in general, as we continue, it will be some number, let's say A. A is generally going to be the number that we use for the number of splits per like number of recursive calls, to some power I times n over b, which is the amount that we divide it, to the power of I. And then each time we make one of these calls, right, it's going to be the size of the thing, and just linear in that size of the thing. Sorry, I'm getting ahead of myself. But it's just going to be that amount for each one of these levels. So what I can do is I can say overall the runtime of this is going to be, if I sum up every single one of these levels, it's going to be the summation of AI over N over BI. This is like a general form, but we know in our case this is just going to be the number of times that we split it is 2, and the amount that we split it by is we have them, so that's going to be 2. And of course, these cancel out, so it just becomes sum of just n, right? And how many times do we sum it? How many layers are there? We log n of these. Why? Because each time we're splitting it by b, which is 2, right? So we're splitting it in half every single time until we can't do that anymore. And the number of times that I can split something in half is log 2 of that thing. Cool, so this is going to be summation of log 2 of n of these, which you should pretty easily be able to tell, is just going to be n log n. So that's, as a reminder, how we got to n log n for this. And we can see that this came out of just looking at this recurrence, finding some summation, and then figuring out what that summation is. Now, this one is a particularly easy problem. Let's look at something a little bit more complicated, and then we'll look at something a lot bit more complicated. Okay? So, next up, let's imagine a slightly different algorithm. Let's imagine instead of sorting the entire array, we want to just find the minimum. Okay? So if I just want to find the minimum of the array, there's plenty of things I can do, but let's imagine I want to do this as a divide and conquer problem. This is sort of it's not a very interesting divide and conquer algorithm, but I just want to use it as an example here. So let's imagine what I do is in each iteration of my algorithm, I split it in half, and then when I do my merge, I only return the top half. So I only return the n over 2 largest elements, or smallest elements, sorry, I'm finding minimum. Smallest elements, and then I discard everything else, and then I recursively call on that. Okay? So what my merge is going to be combining them, right? And I'm only going to take the top half of them, and then I'm going to recursively call on just that top half. Okay, does that make sense? Okay. So here's another way to visualize what I'm talking about. This is like the top-down level. I'm going to go in the other direction. So I'm going to say, in the basic case, I can have all of my individual elements. I'm going to compare them all with each other. I have one more just thing I'll compare. Compare them all with each other, and then whichever is bigger, I'm going to discard. So I'm going to discard the biggest one and recursively call this now on just these 3 elements. So this is what I'm talking about. So I'm recursively just taking the smaller half. And I can do that by doing these comparisons. So I do these comparisons, and then I only add ones that are smaller out of this comparison. And I just recursively do this. Okay? So what I'm doing here is I'm making a recursive call. I'm making a single recursive call. So now I've done one call of it. I'm recursively calling it on just this. Right? Does it make sense? And then I'm going to continue doing this until I only have a single element, or I only have 2 if I want a base case like that. Okay? So now, when I'm doing this, what does my recurrence look like? So how many times do I recursively call the algorithm? Yeah?
I think the maximum.
So maximum depth is fine, but how many times do I call, in one single call of my algorithm, how many times does it call itself if I'm doing this? I know I haven't written out a full algorithm, but I'm saying the algorithm is it takes some array, it compares all of the elements next to each other, only takes the ones that are smaller, creates this new list, and then recursively calls on that. Okay? With the base case of when it's 1 or 2, then I just return the smallest of those. Yeah?
N over 2.
So n over 2, you're saying, what is n over 2? So I'm asking just in the individual thing, like merge sort, I would say, calls itself twice, right? So each iteration of merge sort calls itself 2 times. This one only calls itself 1 time, right? So I'm calling it on this full array. I know I've drawn it as like individual elements, but it calls itself on the full array, and it gets back an array of half the size, right? It takes out the top half of them, and then it calls itself 1 time on this half-sized array, and then we continue down, and it will call itself again and again and again. So it will call itself in total log n times, right? That's the number of times I can split it in half, right? That's still the same, but each iteration of it I only call 1 time. Okay, so my recursive tree would just look like this. So I would call 1 time to get something n over 2, right? And then we continue n over 4, and so on until we eventually have a single case, and then we just return that. Okay, does this make sense? Yeah, I know I haven't drawn this out as a formal algorithm, but I just want to give you a sense of like there are different recurrences here, right? So for finding min, I only need to drop half of it each time. I don't need the top half, right? I don't need to worry about all the elements that are larger because I don't need them if I'm just trying to find the minimum. Does that make sense? Okay. So then if I look at this, right, how much work is done at this top level? How many comparisons do I make? Yeah, n over 2, n over 2. So I compare each one of them. We can say this is still order n, but I'll write it as n over 2 just so we can have it. N over 2. Then when I make a recursive call, what's this going to be? When I make a recursive call on something half the size, yeah?
N over 4.
It'll be n over 4, exactly. So each time it's going to get halved. So this one's going to be n over 8, and etc. down to this just being a single call or no work at all if we wanted to find our base case that way. So this is going to be the summation just of n over 2 times I, right? Or 2 to the I times 2. I'll call it 2I plus 1. There you go. And this summation, can anyone tell me what this is going to be equal to? This is log n here. Think about it for a minute. Yeah. I'll give you a second to think about it. I'll say, can someone give me an upper bound on this? Asymptotically, what would it be? So writing this out, I'll say it for a second. So writing this out is going to be just n over 2 plus n over 4 plus n over 8, etc. Has anyone seen this sort of sequence before? I assume this has been seen before. You may notice 1/2 plus 1/4 plus 1/8 approaches 1, right? If we take the n out of here, or take the n factor here. So this we know is going to be upper bounded by n. That make sense? Because we know that as this goes to infinity, this approaches 1, but we know that we're going to cut off at log n of these steps. So this isn't going to go all the way to infinity, so we know that this is going to be upper bounded at the very least by n. Does that make sense? So we can do another little bit of case analysis here, and we can say, okay, this algorithm is going to be split in half each time and going to do linear work each one of these steps, and it's going to remain linear. Now, has this bought us anything? By the way, just so is this algorithm actually got us anything over some other algorithm? Is there a different way for us to find a minimum in order n time? Think about it for a second. I'll give everyone a second to think about it before doing it. I'll let you have this one though when I'm ready. Yeah. Okay. You want to shout it out? Yeah.
You just go to
Just take a single variable, say it's the minimum, go through the list, and if anything is lower than it, set that to the lowest. You have some very small overhead of needing to initialize that to something correct, but this would be a very easy algorithm. So there's another example of we can do divide and conquer algorithms that don't necessarily bias anything. So there's something to be careful about. Is there isn't just this fundamental value in doing divide and conquer. We have to be careful of actually doing less work, actually saving ourselves some time, which isn't always the case. And you can actually pretty easily show also that finding the minimum, I'm going to need a minimum of order n because I need to be able to check every element. Just reading every single element would take order n. So just something to think about how to design divide and conquer algorithms. But we'll see how we can predict what this number is going to be just based off of the splitting values ahead of time. Okay? So now let's look at the more general case. Okay? So now I want to solve this more generally. I want to be able to just design my algorithm and then immediately know what the runtime is and not need to do all of this math. And you'll notice, perhaps, if you work all this out, some of them are a lot harder to solve than others. Some of these summations end up being somewhat difficult. So let's look at the general form. So we're going to have our algorithm is going to take in an initial input of size n. And this input, I'm then going to split a times. Remember I said a is going to be our sort of fanning, the amount of recursive calls that I'm making. I'll use, let's use red for that. So I'm going to call a times from each one of these. So I'll say a times. And this will produce some arrays here, some sub calls that are of size, I guess I had the blue, oh, the blue's over there. That are all going to be size n over b, okay? We'll say that they're n over b size, so that is each one of these subproblems is going to be 1/b as big, okay? So each one of these are going to be 1 over b as big, okay? So all of those are going to be like that, okay? And we're going to say that at each one of these, the conquer step, the individual call, is going to be doing an additional amount of work equal to n to the c. I'll use purple for that, sure. N to the c. Okay? So these are going to be the 3 different knobs that determine the runtime of our algorithm, okay? This is a little bit of assumption. We're assuming that this is the form of some polynomial. This is going to be a pretty good assumption for a lot of algorithms, but there is a more general way to look at this where we say this could be any amount of extra work. If you're interested in that, by the way, also sort of announcement, I'm adding slides on Piazza under the resources tab that have that cover this material. This is from other universities, actually. I just found ones that I like that I think are well connected to this. And there is a more general proof of what we're doing today where this is going to be an arbitrary function. So if you're interested in that extension, you can look at those slides. Yeah. Oh yeah. Okay. Here, maybe I'll draw it a little bit bigger because this is actually pretty important here. So when we're designing a divide and conquer algorithm, right? We're making some call on some input of size n. Okay. And that input, because we're doing a divide and conquer algorithm, is going to recursively call the same function a times. Okay. A times. And then each of those are going to be size n over b, where b is going to be some other parameter of our algorithm. Each one of these are going to be the same. And then each one of these is also going to do n to the c work. Okay? So that is like in the example from merge sort, we had a is equal to 2, b is equal to 2, and c was equal to 1, because it was just linear. Okay? But let's look at generally how we could solve something like this. Okay, if I want to know the runtime of this, if I have some algorithm and I know these 3 values, how could I get the overall runtime of this? Okay, so let's look at the first element. So this is clearly going to be just n over c, right? Is going to be the first amount of work. But how about the second one? Okay, so first up, how many different calls am I making? I'm making a of them, right? So I'm going to have a times something. Now, what is that something? Yeah? It's going to be n over b plus something, right? So it's going to be each one of these, right? This n over b right here. How much work is this going to do? This individual one. It's going to be n over b to the c. Because remember, it is some amount smaller, right? But we're doing n to the c work at each one of these calls. So this is going to be a times n over b to the c. Okay. So now, question for you. Well, maybe I'll do one more step with this. Let's imagine we split one more time. Okay. Then what will this look like? Right. So what will each one of these be? What size will each one of these be? Someone can just shout it out. N over b squared. So if it was, if it's being decreased by a factor of b, then if I decrease it again, it's going to be n over b squared. Okay? And how many of them will there be? How many total will there be? Stand back. 2a. Not 2a. Close. Yeah? A squared. So each one of the divisions will then divide again. So this will be a squared. A squared times n over b. B what? Squared. B squared Still to the c though. So c doesn't change because each one of these, that still is the amount of work we're doing. The way that it's changing is that the size of the problem is getting smaller. Okay, so then the general case. If I do I of these iterations of dividing this, then how much work will I do on the ith division? I'll wait for people to get to it. Okay. Yeah. Exactly. So this is the term that's going to change. It's going to be a to the I times n over b to the I times c. I times c. So now we have this, and then we can get our summation from this. Okay. So each one of these we have, and we know that this is going to go up to what? How many of these are we going to have? What's the maximum value of I? It's going to be log b, because we're still dividing it by b each time. So it's going to be a summation now that is going to be a to the I times n over b to the I, n over b to the I to the c, and there's going to be a total of log n of these, log b of n. Okay, so I'll put log b n here. So now, we had a special condition in our merge sort previously. What we had was that we had A was equal to B to the C. Okay? This is a special condition. I want you to see why it's a special condition. Can everyone think for a second why this should be a special condition when solving this, this summation? Okay? Think if you can figure out why that is a special condition here. What happens if this is the case? Everyone can take a second to think. I want everyone to get there. This one I think is totally gettable. As a hint, try plugging it in. Everyone a little bit more. You'll have a lot of time to think about this sort of thing though today. Okay? Okay? Raise your hand back there. You want to say?
Well,
Exactly. So if we have this, remember this is going to be n to the c over bi to the c. And now, if this is the case, then if we were to plug in either b4a, right, if we replace this with b to the c, then this will be b to the c to the I, this will be b to the I to the c, which are the same, by the way. Those are equivalent. So these two are going to cancel out, and we will end up with a summation that is just the sum of n to the c up to log b of n, which is just going to be what? Going to be equal to what? Yep. Exactly. N to the c times log b n. Okay? If you're worried, by the way, about this base b, there's a little bit of reason we need to care about it today. But for the most part, you can usually drop these when you're doing asymptotics. We usually don't care too much about it asymptotically, but it is required a little bit for some proofs. Anyway, so you'll notice that we had this condition in merge sort, right? Because 2 was equal to 2 to the first, right? So we had that this was our equation, i.e., if we saw our c was 1, this ended up being n times log n, right? So we can get that pretty easily. So we can do, if we wanted to know ahead of time, we could first check this general case. We can say, okay, if we have this condition, then I know it right away. I know it right away. But it becomes a little bit harder. We might have noticed in our other example, we had that, here, I'll erase this. You should write this down, but we'll write it all out again in a little bit. You'll see why. So you can take a mental screenshot, I suppose. You'll get another chance to write it down. We saw with our, here, I'll leave this up actually. I'll leave this with BDI. We saw with our find minimum, our other example we just did today, what did we have? What was the relationship between A and B to the C? A and B to the C. What did we have? What was the relationship? What was the, was it equal? It was not equal. Instead, we had that A was less than B to the C, right? So each time we were dividing it by 2, but we only recursively called one time. Okay? And C still remained 1 in this case, so it didn't matter too much about that. Right? But we noticed that we ended up doing less work in each time, and as a little hint here, we ended up seeing that this summation converged just to n to the c. Okay? So maybe we can reason out something about that. But I'm going to turn our attention now to the quiz. So I'm going to give you a chance to do a little bit of working this out on your own before I give you the answers to this. If you don't have the quiz, by the way, they're up here. Also, what we're going to do with the quiz today is I'm going to do just the true and falses first, and then we're going to do the rest of it after. So just do the true and false now. If you want to do the rest of it at the same time, you can. But I'm going to cut it off a little bit earlier today, and we're going to do 2 sections of it. Okay? By the way, the bonus is on the back. It's 2 stars today. It's a pretty difficult one, but you can earn half credit if you just get the algorithm without analyzing it. Okay? So I'm gonna give you like 5 minutes to think about the true and false. Okay, you can talk to your neighbor about the true and false. We're doing 2 stages today. Like I said.
Oh, it wouldn't be 0 over 0. It's just R. It's R, it's 1 minus 1 is 0 over 1 minus R. So R could be 0.
All right. Then we call it Theorem and true false. We'll talk about them now. The reason I'm splitting it, by the way, is that these results are going to be necessary for the second part. But we'll work through them now. So first up, if R is less, so here's the thing. So if R is less than 1, then this summation converges to O of X. Right? Who said true? Okay. And who said false? Okay. So this is in fact true, and you can see that the general case of this is that as I add these terms, each one is getting smaller, right? That's essentially what's happening here. But it isn't obvious that this should converge. If I is some large value, say I is equal to like n in the example of having something of let's say it's x, right? It's x large, so it can be a bunch of values. It isn't obvious that this wouldn't be something like x squared or x to the x or something like that. But it turns out that it is, and the easiest way for us to tell that is by looking at our value here, right? So if we look at the geometric series here, we can see that if R is less than 1, then as we look at this asymptotically, and when we're doing asymptotics in here, we're looking as I goes to infinity. That makes sense? We see that this term up here is going to 1, and this term is just 1 over R, so that's just going to be some constant, right? So it's going to be 1 over some value that is less than 1. It's just some number. So that's going to be some constant times x. So in fact, this is going to be upper bounded by x times 1, because this is going to be strictly, or no, this is going to be a little bit larger than 1. It'll be bounded by some value it'll be x times some value, sorry. So this will in fact be order x. Less obviously though, what happens when R is larger than 1? So first off, is it upper bounded by negative infinity? True? Okay, and false? So I think it is sort of baiting here because nothing is going to be upper bounded by negative infinity. This is just a little bit of a spot check of that. And also, if you plug it in here, so if you were to plug in the value, then this will go to infinity, right? It'll go to positive infinity as I goes to infinity. This will remain some constant value, and you might say, okay, it's some negative then, but it turns out that this is not the case. And it will converge to something else, which you'll have to work out in a little bit. And I'll give you some clues as to how you might be able to do that. Okay. Yeah, it is not it's not upper bounded by negative infinity. Lastly, there's no closed form expression for when the geometric series when R is equal to 1, or R to the I is equal to 1. Who said true? And who said false? Okay, cool. Some people did not raise their hand for either. I get that. Probably the term closed form might have not. People might not know what I mean by that. Basically, you can only express it with like normal algebraic symbols rather than other things. The reason that this might cause some sort of confusion is if we look at this equation, right, then we see that if I plug it in here, then this is going to be 0 over 0, because the only case when R to the I is equal to 1 is when R itself is 1 or imaginary, which we're going to pretend that doesn't exist. In which case it would be 0 over 0, and what does that equal to? And that is difficult. But if we look at the other half of this, and we were to plug it in, all of these R's are just going to be 1, so it's then going to end up being just I times R, or I times X, sorry, I times X, because each one of these is just going to be X, and there will be I of them. Does that make sense? So there is, in fact, a nice closed form solution for that. Okay? So now we have a little bit of experience with this. Yeah? Question? So that's a good question. So R is going to be bounded between, R is going to be positive, so we're going to say it can't be 0 and it can't be negative. This geometric expression is only for those cases. You can have other things that will converge differently, but if we allow for negative, then the whole thing will just be negative of that, because or it won't be exactly. Never mind. Take that back. Because if we have negative, then it will alternate between positive and negative. There's different convergences for negative numbers. Yeah. Okay. So now we're going to try to solve these equations We're going to try to solve a recurrence using this little trick. See if we can figure anything else out. There is also a couple useful things that are going to help us, right? Which are going to be a couple log rules. I'm just going to write up here so that everyone has them in case you don't know them already. Here, let me grab my notebook so I don't mess these up. They're not particularly difficult, but people might have not seen them in a long time or ever. So we have a couple rules. One, we have that log, let's say, a of b is equal to log a of n times, I'll use a different, I'll say c. These are going to be different a, b's, and c's than you actually will have in the problem, by the way. Sorry for choosing the same values. Times log c of b. So you can sort of chain together logarithms like this. That makes sense? Cool. And the only other one is that some value to the, like I would say, a to the b to the c is equal to a to the b times c is equal to a to the c to the b. There's a fun little exponent rule that you might not know. Yeah?
But these things also run the first layer, right?
Which one?
No, when I see this, the first thing I think is, oh, first you're doing b to the c, and then...
Yeah. I mean, there's different ways you can, yeah.
Oh, no, but like to make it clear, I guess.
Oh, okay.
Never mind.
Okay, yeah, no, it's a raised to the b raised to the c is equal to a raised to the b times c is equal to a to the b raised to the c. Just if you never notice that about exponents, that is actually true. Kind of neat. This first one is just a logarithm rule. This is like the definition of based logs, actually, but I've rewritten it in a way that will be useful for this problem. Okay, now with those, this one is going to be a little bit harder. It requires some creativity. Some of them are easy, some of them are hard of this problem, but you need these rules for the hard one. Okay? So again, take your time with this now, and then we're going to do come together afterwards to explain. very explicit, by the way, this is what we solved earlier. We said that T of n was equal to this. What all this work was for. In case anyone missed that. Okay, I'm gonna allow you guys to talk to each other now. I'm gonna spend a little bit more time on this one. You guys can spend like 10, maybe 15 minutes for this. I do want you to try to really actually solve this one though. Okay? I'll be coming around. If you have questions or you want any hints, ask me. I'll be giving them out.
It's just a lot of like logs and whatever. Like, I'm not sure.
But I like do you understand the first part? Were you
So that part's actually
Oh, never mind. I just realized you wrote the dot problem.
Yeah, you're good.
I got it.
No.
So yeah, that's like another way to write this.
Did we not have to find the like the map?
I like did all the stuff. And I turned that into a summation. Summation is the same thing.
Yeah, so instead of high copy, start at 0.
Yeah, once I this annotation is not that hard. It's shove it in. Essentially, it would just look like I think this is I just don't know. I just additional copy. But it's on my scribble on the side. It's on the outside.
No, I did the same thing every time.
So then that's what this is, and then you can use that second rule that he gave us to, well, first you distribute the seed, and then you multiply this here, right? And then to make the geometric series, we just want to have one thing next to the j, right? So we put the a and the b together, so it's just like the bad version of it. But we just put a over b into the seed, right? And then we use that like the rule again that he gave us, but in reverse to take the j out.
So just for each of these.
Oh, also, if you're wondering where the seed went to,
Yeah.
I took it out of the whole thing because it didn't rely on it. So, like, pretty much, if I just look at what I did at the inside, right?
Oh no, this one's alright. That was your these two are both putting that form is important. Like the way that I recommend it, find the balance for general answer. And then go for me. That's a more analysis. You'll see my way of solving it in a little bit, and you decide if you go for that.
You just take out because
That's how I suggest it.
this n over 1 times 1 over b. They're equivalent. So as long as you multiply, it's good. And you can just I'll just go write it out. So you have 1 to the b, n over 1. That's the same. after you simplify the C, you just might do and then it comes kind of yeah. No, you're talking about where the C went. I was giving you the algebra.
I don't know how to use that.
Well, the one that's up there.
Yeah, but it's like a little mistakes.
No, and that's why I think we're wrong. That is precisely why.
Oh, that's the computing development.
Yeah, I mean, it's not. During my work.
No one's going to be. I tried to make it so that one would be on finance. They like I just do on my own.
No, you're basically just, you're along for the ride. Like if you were to make this would be the 1 over B.
Our R is A over B.
Oh, okay, yeah, that makes sense.
Because, yeah, just like
Then what's the X?
yeah, and our X is N to the C. That's what like I started working on. I agree.
Yeah.
And then same like the case where R is greater than 1 is going to say A is greater than 2C. Oh! Oh, that's what we had earlier. Yeah. Well, yeah, I still don't know how to use it.
Where is this all to?
What could it possibly be?
Yeah. Like you don't. Yeah. It's a choice, and it's like.
but this form is not particularly. I think actually I'll make it a napkin. Hey everyone. I'm just going to give a sort of broad hint. I've been using it a couple of times. I want to make sure everyone has this hint. So once you put it in geometric form, which I'll say this right now. Where's my markers over here? You can rewrite this in geometric form. I'm just using one color. Sorry about that. You can say that this is just n to the c times a over b to the c to the I. Okay. So this is a geometric form. We'll use summation of it. Sorry. You say this is summation of this. Okay, so we can put in geometric form like that, just if you haven't had it properly in geometric form, there you go. And then from this, we don't want to rewrite it the way that we have our geometric form written out over there. Instead, we want to solve the bounds for a generic geometric series and then apply them to this. For example, our first true and false, we say that if r, which is this term, so we say a over b to the c is less than 1, right, then we know that it's O of x. And x in our case is going to be n to the c, therefore in this case it is order n to the c. So that's an example of one of the cases. The other cases are slightly more difficult, but I will allow you to try around. The other cases, by the way, are a over b to the c equals 1, which is we've seen before, and then a over b to the c is greater, or is greater than 1, which is the more difficult case. So this one's the hardest one. And to get into nice form, you have to use those. Yeah. Okay, you continue. If you're done with these, by the way, I better see you working on the bonus. Yeah, continue. I'm trying to write a signal.
Oh, it cancels out.
So these give you different results. Each one is different. Yeah, this geometric series will convert differently depending on the value of r. That's sort of they're all different. It comes from this case. Greater than 1 case.
Okay, that's fine.
So this will go towards infinity, right? So then you can solve it. So what is it? this is an actual log. So he doesn't actually require anything. You need to worry about the maybe the reason we do this is but we're doing the asymptotics in and so we know this exactly
Sorry, just a quick question.
I did like the previous bonus only had to be one. But I took out my final.
we did this one. Just did the equality.
Yeah, I did the equality. But I took out 8 and I took out the C and the log of 8. I just did log and
Yeah, so with the log, if you're doing asymptotics, the log is asymptotically log. There is very niche cases where we care about the case, but it's not. So C is some value, but n to the C.
right.
This is the merge,
So basically, yeah.
So this is really just
I don't know how that helps. Yep, I like that.
so that's
Yeah.
I think that could get us a B and A. Oh yeah, is it offset? Oh, and then the -1 comes in. That's
Oh yeah.
Yeah. Did you know that log is so you get like
So you're looking at as I goes to infinity, which so we were doing that. Okay, so I perhaps misled you. We're doing that because we're upper bounding. Like we know that as I goes to infinity, that will be an upper bound. It's not because that's actually what the condition is. We care about asymptotically with respect to us in this solution. Instead of I going to infinity, the maximum I is long. That's like our summation right there. It's long.
that's not necessarily.
Yeah.
This is what I have. I just used this.
Yeah, I mean, so I don't know if it's really nice for
I used one of the log rules where you can rewrite this as this. I don't know if
so first off, I guess whatever log rule I have is the power of log b to x is equal to x. So you can start with that.
b to the power of log b.
So if I have like b to the power of log b of x equals x.
So yeah, we distribute.
Yeah.
Okay.
You end up with a really nice form.
are you doing this? Yeah, that's it's the same one for all of them.
Yeah, I
I mean, just treat it like treat it that. I mean, like just treat it. Solve them log and then minus 1.
solve for so minus 1 and then so when you plug, so I think I'll be explaining it now. Yeah, no, I mean, it requires it's helpful. I think that's when I do the explanation, it's probably. So I'll wait on that.
How do I call a whatever? Like it has to be someone else.
That feels right. Like,
Just what I did is I just distributed this. Well, first I switched this up because
yeah.
so I swapped this and then I distributed it. A to the log B and over this, right? And then use that rule that he just wrote out. D log B, this is going to just equal n over B.
Yep.
Put that to the C. And then, oh, I can still do some more. So I just so it's going to be equal to the C. That's perfect. So that's going to be B, A, C, log.
Yeah.
It's a power. Everything after the everything after
Okay, let's go through the proofs now. All right, so we have our 3 cases over there, and now let's try to find tight bounds on all of them. So first up is the so we have the less than 1 case. This one we already have locked down. We know that it's upper bounded by MC at least. We'll also notice that when we actually solved it previously, the equation we got was n to the c, right? It was just n to the c. So in fact, this is going to be a tight bound. This theta, as we remember, means that's an upper bound and a lower bound. So the reason that we have that is just because the actual formula was n to the c. It's pretty obvious to see that that is upper and lower bounded. I know this is somewhat new notation, but as long as it's within a constant of something, it'll be an upper bound and a lower bound to it. Okay. So the other 2 cases are slightly more difficult. So let's look at the first case here. So, or I guess the first or the second case is not. We did already kind of do this, so hopefully it's not too bad. So if a over b to the c is equal to 1. So this is exactly our case before, where they're exactly equal. I'd say that this is probably the nicest way for us to be able to do this convergence is just plug them in to this equation directly. So if we have that, right, then this is just going to be a summation. And remember, what we're summating over here is log bn still, right? Log bn. So we're just going to have a summation of log bn up to log bn, where we have these. And if I plug this in, then I'm going to get n to the c times 1 to the I, which is just going to always be 1. So I'm going to remove that. And here we can see pretty easily that this formula is just going to give us n to the c times log bn. And if we are writing this in asymptotic notation, we can drop the base on the logarithm. It's not exactly equal, but we usually don't care about it too much in asymptotics. This is just going to be theta n to the c times log n. If you want to be more proper, you can write in the b, though. The b is implicitly there. We just usually don't care what base we're in because we can convert between bases for a lot of these things. Anyway, I have that. Cool. So this one basically just came from a previous result that we had. We can just plug in this in directly based off of the case. Okay? Any questions on this one? Okay. Then we can talk about the slightly more difficult case. Yeah. So what allowed me to take it over is, so this is, like the variable here is I, right? I equals 0 to this. This does not depend on I. So I'm just summating log bn copies of this term. Right? Does that make sense? And that is just going to give me a multiplication. So if I sum n 5 times, that equals 5n. Same deal here. Yeah. Cool? Cool. So now the slightly trickier case that I think is the one that people might have missed, which is when this is greater than 1. Okay. So I'm going to go through it so you guys have the proof of it. Yeah. So this is greater than 1. When it's strictly greater than 1. So what can we do? Well, first off, what we can do is we can. Okay. Let me decide how I want to do this. Okay. So first off, what we can do is we can look at our geometric series. Right. So our geometric series, we have our summation here. So I'll just say it's we have our summation of x r to the I, and this approaches x times 1 minus r to the I over 1 minus r. Okay. And now let's consider. Okay. Let's consider what the upper bound on this is. Did anyone get what the upper bound on this is? Anyone? I think I see a hand. Yeah. Yeah. I thought you were raising your hand. What?
Up to infinity.
So that would be as I goes to infinity, but I isn't going to infinity. I is going to be up to log b of n is what we're really going to care about. So the way that we can think about this is basically as we go through the summation, every term is getting bigger, right? If we have r is greater than 1, then as I add these terms, every term is getting bigger than the last. So in the previous case, where we had that every term was getting smaller, what we noticed was that the first term was the biggest term, right? And it turned out that asymptotically, that was actually what it was equal to. Now, the same logic applies in reverse here. If we have some set number of these, then as it gets smaller each one of these steps, or as it gets bigger, sorry, as it gets bigger each one of these steps, then the thing at the very end is going to dominate. So in general, we actually have, so here I'm gonna just do something real quick. I think we can talk about this more in like office hours if people don't understand this concept very well, but the basic idea is if I have multiple functions, right? If I have some constant number of functions, if I have like let's say f of n plus g of n, etc. They keep going. I have some summation of these. If I want to tightly bound these, and I know that f of n is strictly larger than g of n, so if I know that f of n, or if f of n is an upper bound on g of n, I'll write it the other way. So g of n is upper bounded by f of n, and we also know that that f of n is not upper bounded by g of n, so they're not equal, but f of n is strictly bigger. Then I know that this, if it's bigger than all the rest of them, then I know that this is actually going to be exactly equal to f of n. So this is something like if I had x plus x squared plus x to the third up to x to the 10th or something like that, then asymptotically, this term is the only one that matters. Everything else I can discard. This is the only term that matters because it grows the fastest, right? And it's very similar thing is applying here, where the only term that ends up mattering in this entire series is the last one. Okay? We can also see this from